Okay, yes. So hello all, and thank you to GTT for having me today to present some of the work that we've been doing at Forschungszentrum Jülich, mainly regarding database development and thermodynamic modeling. So I'll be presenting this work on behalf of my colleagues, myself, Maria, Victoria, Amadeo, Sue, Ja, Elena, and Mikhail. So as we've all heard, thermodynamic databases are key to understanding the behavior of materials in complex systems, in which small changes in conditions can result in very large changes of the system behavior. So this can be seen in many applications. Only investigation is unfeasible. So the combination of experimental facilities we have at Forschungszentrum Jülich, coupled with our developed thermodynamic databases, are able to give a deeper insight into material behavior and formation. So on this slide here, we can see an overview of the CalFAT approach, which is used for our database development. So in the initial steps, we collate the thermodynamic data on the system, so including phase equilibria, enthalpy of mixing, formation, and so on. We can also do activity. So next, we choose the initial data for the substances within the system. So this usually involves looking through literature and other databases for this information and choosing the most appropriate. So lastly, we choose the appropriate model for the solution phases. At Forschungszentrum Jülich, we mainly use the sublattice and associate species model so that we have a consistent database across all material types, as will be shown later. So next we move on to the enthalpy and entropy terms. So these can also be optimized, but in general, what we mainly look into are the interaction parameters. And so these can be optimized using the CalFAT optimizer available as part of the FactSage software package, and will also be discussed a bit later this morning, I think. So finally, we compare our calculations to the literature and some of the experiments we can also conduct at Jülich within our labs until we are satisfied that our predictions match what we can see in reality. So as previously mentioned, in order to verify our databases, we regularly compare to experimental work. So at Forschungszentrum Jülich, we're quite lucky enough to have world-class research facilities which allow us to generate much of the data which is necessary for our work. So phase equilibria, transition enthalpies, and specific heat can be measured by one of our many calorimeters across a range of temperatures. So from, minus 150 degrees Celsius all the way up to 1600 degrees, sometimes even more, also under a range of different conditions. So we can also measure activity and formation enthalpies using Knudsen diffusion mass spectrometer, which is also quite special. But in addition to the thermodynamic data, we also can generate crystallographic and structural property data using XRD, high temperature, XRD, and SEM EDX. So this brings me to the first project I wanted to speak about, and that is the FESTES project. So in this project, we're aiming to develop high temperature solid-solid phase change materials for thermal storage applications. So as we've seen on the next slide, the project was open for all material types, but we mainly focused on sulfates, tetrafluoroborates, and oxides. So this project is a consortium of ourselves, GTT-Technologies, TU Munich, and Pavel Heater, who is a thermal storage construction company. So as we wanted to identify solid-solid PCMs, which could be useful for our stated application, it was natural to partner with GTT-Technologies to explore their material databases for materials of interest. So this involves searching for materials with a high solid-solid transition enthalpy and a solid-solid transition temperature between 200 and 800 degrees Celsius. So using the information contained within these GTT databases, we screened over 500 different compounds and then selected the 40 most promising, which can be seen here on the slide. We then did some further investigation into these materials and screened out materials which were too high cost, were found to be unstable or toxic, and then that left us with a list of roughly 11 materials to be further characterized. So on this slide, we can see some of the thermal characterization of these materials of interest. For thermal storage applications, obviously, in addition to the high transition enthalpy and appropriate transition temperature, we're also looking for materials which have a high thermal diffusivity, high specific heat, and low thermal expansion. So on the left-hand side, we can see the thermal diffusivity of sodium sulfate. And as we can see, if we actually use sodium sulfate as a pressed pellet instead of a powder, we can greatly increase the thermal diffusivity, which obviously helps to make a more efficient thermal storage system. In the middle, we can see the DSC signal from lithium sulfate. So we measured the specific heat. And as we can see, DSC, giant melting peak around 570, indicating the solid-solid transition, which correlates well with our prediction and what we can see in literature. So on the far right, we can see the thermal expansion of potassium tetrafluoroborate. So while the total value of thermal expansion is the same, we can see whether we have it in a pellet or in powder form, there is a slight difference in how that thermal expansion actually behaves. So using all of this data, we're then able to obviously generate more accurate thermal storage designs. So in addition to the pure compounds identified from the screening, we also decided to look at binary mixtures of some of these compounds to see if they could also be useful as solid-solid PCMs. One of the more promising compositions or combinations that we found was from the sodium sulfate, sodium tungstenate system. So we can see on the right-hand side the previous phase diagram, which kind of showed a composition-dependent solid-solid transition. But if we actually look on the left-hand side from the DSC signals, we can see that as we change the composition, it's actually just a relatively standard, relatively stable solid-solid transition. So this kind of highlights the need to continuously recheck the data that we have within our databases or literature to try and see if these previous results are still valid. So the next project I wanted to talk about, so while the first test project used existing databases to screen new materials, the PCM screening project was mainly aimed to develop our own database and then screen for promising solid liquid phase change materials. So this database contains alkali and alkali earth materials, including nitrates, sulfates, chlorides, and carbonates, and was performed alongside GTT, BTU, and TU Dresden. So while the vast majority of the binary systems have been experimentally investigated at Forschungszentrum Jülich, I just wanted to present some of the results from the calcium sulfate, magnesium sulfate system. So this system was particularly difficult to obtain reliable thermodynamic results because both of these sulfates tend to decompose when heated up at higher temperatures. So to overcome this, special double-walled platinum tubes were fabricated in order to be able to generate that data at high temperature. So while not shown here, the previously assessed phase diagram actually looks very different to what you can see on the top hand right. And this was due to originally there was thought there was a compound of the magnesium calcium with a 3-to-1 stoichiometry. However, when we did the further study, it was actually found that this compound had a stoichiometry of 2-to-1, and therefore we spent a lot of time trying to synthesize this material, as you can kind of see on the your left-hand side, my right-hand side, in order to generate the data and to try and prove that it does exist in that 2-to-1 stoichiometry. So once we had this data, we were then able to add it to our database in order to generate the phase diagram that you can see here on the top right, which better represents the experimental data that we have for that system. So similar to the FEST test project, a screening of the database was then undertaken to identify the materials of interest. So on this slide, we can see the two systems that we screened, so namely the sodium, potassium, calcium sulfate chloride system and the sodium, potassium, sulfate chloride carbonate system. So several promising compositions were suggested from this screening. I've just chosen two here that we can see. So on the top, we can see, or actually on the far left-hand side, you can see the phase kind of description, which shows congruent melting between kind of 450 and 500 degrees. If we can look at the DSC signals on the top, you can see, especially during cooling of the top system, that there are two peaks in the DSC signal, which kind of indicates that it's non-congruent melting, which is not what we want for the PCMs. However, if we look on the bottom, you can see that there is only one strong peak in the DSC signal, showing that we have congruent melting and that we are able to predict a multi-complex system in order to identify phase change materials of interest. So this kind of gives us hope that this methodology is a valid way to screen multi-complex systems. So the last thermal storage project I wanted to talk about was the SaltMe project. So while the other projects mainly investigated salt-based materials, this one actually looks at salt and metal combinations. So one of the drawbacks of salt-based thermal storage systems is that the thermal conductivity or thermal diffusivity is relatively low. But it's hoped that in adding a metal to this system, we can actually increase this thermal conductivity and have more efficient thermal storage systems. So this project was mainly done between us and TU Dresden. So here we can see some results from the sodium metal and potassium chloride system. So from the DTA signals on the far right, it can be seen that we form a eutectic between the sodium metal and the sodium potassium chloride at around 10%. So as we continue to add sodium metal, we start to have more of a two-phase region, which you can see on the phase diagram to the right. So you can see that the experimental results match quite well the phase diagram that we're able to predict using our database. So we also looked at the diagonal of the system between the eutectic of the sodium chloride, potassium chloride, and sodium metal. So again, adding sodium to the system, we can form a eutectic between the three components, which again corresponds really well to the phase diagram that we're able to predict. I will say this is also, like the double sulfate system, quite difficult to explore experimentally because of corrosion issues and stability issues of the material. And that's why there was also quite a lot of investigation done on finding appropriate crucible materials and crucible configurations. But nevertheless, we have been able to solve that in order to generate the data that we have there. So lastly, I wanted to present some work on some non-thermal storage related systems. So for this, we have the Vera and Verena projects. So these projects are similar in that they investigate fuel ash systems, which are common in gasification, for example. So this is mainly oxide chloride and oxide carbonate systems and is undertaken with a range of partners. Here so you can see there, so TUM, Darmstadt, Freiburg, Stuttgart, and GTT as well. So on this slide, we can see some of the work that's been undertaken on the potassium oxide chloride silicon dioxide system. So what was particularly interesting for us was the experimental verification of compounds in the potassium oxide rich side of the potassium oxide silicon oxide system. So using the XRD, which is not there. We are using an XRD, but the XRD is not shown there. We can see that the K4SiO4 and K6SiO7 were found. But furthermore, when we exposed the potassium silicates to potassium chloride, it was found that K2SiO3 that readily reacts, as you can see kind of in the phase diagram on the top right. But the same cannot be said for the K2SiO5 system, which was found to be too viscous to react in the time for the experiments. So on this slide here, we can see some of the work undertaken on the, did that one go through? No. Okay. If it goes through. Yep. Okay. So a similar study was also performed under a CO2 atmosphere. Was found under these conditions that K2SiO3 can be transformed to K2SiO5, which then further reacts with the potassium carbonate. However, if we perform these experiments under argon, this transformation does not occur, as seen in the high temperature XRD profiles at the bottom there. So this information has allowed us to update our understanding of the phase diagram, which you can see on the top right-hand side. So other material systems have also been studied, such as the calcium oxide, silicon dioxide, calcium chloride system, as you can see on this slide. So again, this system is a particular challenge because of the high temperature melting of calcium oxide and silicon dioxide compared to the calcium chloride, which makes it hard to obviously react these components. Nevertheless, preliminary results show that there is no reaction between the calcium chloride and silicon dioxide under argon. However, we have non-equilibrium ternary phases formed under air conditions, as can be seen in the XRD figure at the bottom there. So we've also updated some of the data in the GT-OX database to better describe the sodium chloride phosphate system. So for example, the decomposition of the compound NaPO3 NaCl can be better described, as you can see on the bottom left there, while the NaCl Na4P2O7 system is modeled and is in good agreement with what can be seen in literature. So finally, we can also model the sodium chloride Na3PO4 system, which can be predicted there, even though there is no experimental data on that system. So even if we don't have data on the system, we're still able to form quite good and hopefully accurate phase diagrams. So lastly, an overview of another interesting system can be seen here, which is the sodium carbonate, calcium carbonate system, which is on the left, while incongruent melting of the calcium oxide, calcium chloride system is modeled alongside the system, the liquid phase. This can be seen in the middle. So this is all new data. While compound property data in the calcium chloride, calcium phosphate system is also being generated based on previous experimental data. So all of these systems have been added to the GT-OX database now, enhancing the thermodynamic description and predictions of this database. So finally, an overview of the materials contained within our database can be seen here. So over the past years, the database has obviously grown quite considerably, expanding the information on oxides while also including new materials such as salt and metal species. So due to this, complex phase equilibria can be reliably calculated, even when the experimental data is missing. So additionally, using the SLIC model, various systems can also be calculated all within the one database. So moving forward, we're going to continue to add new materials and experimental data to the database to improve our predictions and the understanding of complex systems. So in turn, this helps us to support and reduce material development costs, especially for applications such as thermal storage, batteries, fuel cells, electrolysis, and gasifiers. So that brings me to the end of the presentation. Happy to answer any questions.